Okay, so today we are going to talk about more tests that we can do to determine if a series converges or diverges. But before we kind of dive completely, well, I guess our first one we want to talk about is our direct comparison test. So the direct comparison test just tells us if a sub n is greater than or equal to 0 and b sub n is greater than or equal to 0. If b sub n converges and is greater than a sub n, then a sub n is also going to converge, right? And if a sub n diverges and is less than b sub n, then b sub n is going to diverge. And I think this makes sense if you really kind of think about it. Like a series that is less than another one, well, if the smaller series is converging, then that bigger series, or if the smaller series is diverging, then the bigger series must also diverge. And if the bigger series is converging, then that smaller series must also converge. So when you're doing this, you have to show the inequality when stating the conclusion of the test. So we'll do a few to kind of go through it. So here we're asked to determine whether the following series converge or diverge. So for number 1 here, we should actually always do the nth term test first, probably. So I'm going to say the limit as n approaches infinity of n cubed over n cubed plus 1. Well, that's equal to 1. That's not equal to 0. Therefore, this diverges. This diverges by the nth term test. All right, let's look at number 2 here. So if I'm just going to do this nth term test real quick in my head. I get 1 over basically infinity, which basically becomes 0. So this might converge, right? So we're going to compare it to, we want to compare this to the sum as n equals 1 approaches infinity of, let's do 1 over n cubed, okay? That is going to be a p-series, right? And this is a convergent p-series. So a convergent p-series, and we know that because our p3 here is greater than 1, so we know that this converges. So since 1 over n cubed plus 1 is less than or equal to 1 over n cubed, for all n greater than or equal to 1, and this converges, then the sum is n equals 1 to infinity of 1 over n cubed plus 1 also converges. Okay, right? So since this is smaller, the bigger one is converging, then the smaller one must also converge, right? All right, let's look here. We have the sum from n equals 1 to infinity of 1 over 3 to the n plus 2. Well, we're going to compare this to, the sum from n equals 1 to infinity of, let's do 1 over 3 to the n, right? So this is going to be smaller. This is a geometric series, right? So this is the same as, which is equal to, n equals 1 to infinity. I shouldn't have written it like this, but I ran out of room. And so this is a convergent geometric series, right? So this convergent geometric series, because our r is less than or equal to 1, right? So, and greater than 0, since 1 over 3 to the n plus 2 is less than or equal to, now it's going to be less than because, right, as you add more terms, that denominator is going to get smaller, and then it's a smaller number, less than or equal to 1 over 3 to the n for all n's contained, greater than or equal to 1. Since then, the sum of this original series also converges. Okay? All right, let's do this one. We have the sum from n equals 4 to infinity of 1 over square root of n minus 1. What do you think we can compare that to? Well, let's compare it to the sum as n equals 4 to infinity of 1 over n to the 1/2. And this is going to be a divergent, p-series, right? Because here, p is less than 1, so we have a divergent p-series. So since, now this, 1 over n to the 1/2 is less than or equal to 1 over the square root of n minus 1, right? Because we subtracted here, so this is actually going to be bigger than this for all n greater than or equal to 4. Then this original series also diverges, right? So because our smaller one diverged, that divergent p-series, our greater series is also going to diverge. All right, let's do one here with a little bit of trig. Okay, we have from n equals 1 to infinity of cosine of n over 2 to the n. Well, we can actually, so if you think about cosine of n, what's kind of happening with that? It's going up and down, negative 1 to 1, negative 1, negative 1 to 1, negative 1 to 1. So it's really just between 1. So we can compare this to the sum from n equals 1 to infinity of, let's just compare it to 1 over 2 to the n, right? And that's going to be equal to 1/2 to the n, whoops. And this is going to be what? A geometric series, a convergent, that converges. Oh, I didn't write this well. That converges. What a mess. All right. So since cosine of n over 2 to the n is less than or equal 1 over 2 to the n. Now we know that's true, right? Because cosine is never going to be completely 1, right? It has to be less than or equal to, or actually even if it is equal to 1, it's okay. It can be equal to it for all the n greater than or equal to 1. And this converges, right? Then this also converges. Then the sum from n equals 1 to infinity of cosine of n over 2 to the n also converges. Okay, so we have this. The sum from n equals 2 to infinity of 1 over n to the 4th minus 10. Let's compare it to the sum from n equals 2 to infinity of 1 over n to the 4th. Oops, I wrote 3rd, but I meant 4th. 1 over n to the 4th. So this is a convergent p-series. Convergent p-series. And since 1 over n to the 4th minus 10, well, I was going to say that that's less than or equal to, but that's not actually true, right? So if we compare this, we've kind of got a problem here, and we need to use another technique. Well, we can use another technique. We're going to use a limit comparison test, and that's what I'm going to talk about now. So the limit comparison test says that if a sub n is greater than or equal to 0 and b sub n is greater than or equal to 0, and the limit as n approaches infinity of a sub n over b sub n is equal to L, or as it b sub n over a sub n is equal to L is both finite and positive, then the two series either converge or diverge. So they're either they're both going to do the same thing. So let's do some examples here. We have the series from 1 to infinity of 1 over 3n squared minus 4n plus 5. Let's compare this to, the sum from n equals 1 to infinity of 1 over n squared. And notice that we're using kind of like simpler series, right? And this is a convergent p-series, right? So I'm going to rewrite this as the limit as n approaches infinity of, well, this divided by this is just going to become n squared over 3n squared minus 4n plus 5, right? And if I find the limit of this, I'm going to get 1/3, okay? Is 1/3 finite and positive? Yes. So the sum n equals 1 to infinity of 1 over 3n squared minus 4n plus 5. I'm running out of ink here. This converges, also converges. I gotta change my pen, 1 second. Okay, I switched to red because the blue ran out. So here we have the sum from n equals 1 to infinity of n to the 4th plus 10 over 4n to the 5th minus n cubed plus 7. Well, if I whittle this down to kind of its most basic form, I'm basically going to get 1 over n, right? So I'm going to compare this to the sum from n equals 1 to infinity of 1 over n. What is that sum? That's our divergent harmonic series. The divergent harmonic series. right? And I got this by simplifying here, getting rid of all of that. So if I find this limit, I'm going to have the limit as n approaches infinity of n to the 4th plus 10 over 4n to the 5th minus n cubed plus 7. This is times n over 1. This is basically, I wrote n over n, but I meant n over 1. This is basically going to become like, this would be n to the 5th, right? So n to the 5th plus 10n, like, so I'm going to get 1/4 here. Is that finite? Yes. Is it positive? Yes. Therefore, this sum from n equals 1 to infinity of n to the 4th plus 10 over 4n to the 5th minus n cubed plus 7 also diverges. Okay. 2 more examples and we're free to go. The sum from n equals 2 to infinity of 1 over n cubed minus 3. Well, I'm going to compare this to the sum from 2 to infinity of 1 over n cubed. That's a convergent p-series. Hopefully you're kind of starting to recognize your p-series here. So if I get my limit as n approaches infinity of, if I divide this, I'm going to just end up with n cubed over n cubed minus 2. Well, that's equal to 1. That's finite and positive. Therefore, that sum, our original sum of 1 over n cubed minus 2, is also convergent. Okay? Let's do one last one here. We have the sum from 1 to infinity of 1 over the square root of 3n minus 2. Let's compare that to the sum from 1 to infinity of 1 over n to the 1/2. That's a divergent, a divergent p-series, right? A divergent p-series because our p is less than 1. So if I divide here, I'm going to get my limit as n approaches infinity of the square root of n over the square root of 3n minus 2, which I can rewrite as the limit as n approaches infinity of the square root of n over 3n minus 2. And that is equal to, be very, very careful here, it's not equal to 1/3, it's equal to the square root of 1/3, right? Don't forget you've got that square root happening there. So this is finite, this is positive, so the sum from 1 to infinity of 1 over the square root of 3n minus 2 diverges. Okay? Some useful tests that we learned today. Hopefully they help you out. If you have any questions, leave them in the comments.